Like I don't remember putting to it.
Why can't I not log in?
All right.
So you actually have to.
Alright. Well, I have some idea of these now.
Actually, like this is really simple, but do you have to like do this like airplane help? Or like it'll let you go to like.
Very pretty
Are you a medical examiner?
I kind of go to this.
Oh.
Oh.
If you kind of like keep going through this, it'll eventually.
Wow. Sucks.
Doesn't matter. I just kind of click through things, and eventually it'll tell you to do something.
Okay. Thank you.
All right, so let's breeze through the sort of conceptual part of logistic regression. This is, it's lab, so we'll do the how-to part, right? So we know that logistic regression is used a lot, blah, 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 blah. Okay, good, that's good. All right, we did this. This is something that I tried to impress upon you when we were talking about the theory. So first to use regression, right, with a binary variable. The binary variable is going to be 0 and 1. We have to somehow transform it into the negative infinity to positive infinity space that we dealt with regression. And we talked about different ways of doing it. We talked about probit regression, but another way to do this is logistic regression. Okay. And what we see here in the middle of the, inside the parentheses is we have probabilities. Probabilities we can convert to odds. This is how we convert probability to odds. And we take the log of those odds to get the log odds or a logit. All right, okay, and this becomes our familiar model. Right? We talk about maximum likelihood being this idea of a bunch of gauges being turned one at a time. We talk about how to interpret our betas as odds ratios. So, do you guys have a computer in front of you? If you have a computer in front of you, let's do this exercise together, okay? So I'll let you grab that. While you're typing that, I'm going to go see some more copies of it.
Is it working?
Yeah.
Oh, we're just trying to.
Give me a
Oh. It said it's not found on the server.
I think it's in theory.
So I got to this page, but it says, right? But then it says when I click on it, it says
Oh,
it's
type that in Stata.
type that data.
Stata.
Are you using it? I have no problem. What are you typing it in?
I'll type it in the browser. My like. I saw a URL. I was just going for it.
My connection timed out.
Well, I take it off fast.
You take what off fast?
My stethoscope, if it's around my neck. I don't like that. I don't like anything around my neck. I'm over turtlenecks and that's it.
Oh, I'm completely, like, I'm hacked it.
I have a scarf, so I can put something around my
Oh,
neck.
yeah.
I wish we could combine our genes.
Do you think that's a genetic thing? You might be overestimating.
It comes from
It's
the
not,
gene.
my connection keeps timing out. So
Oh, I got it.
Let me download it. Are you guys able to download it?
Yeah, I just got it.
Alrighty here. All right. Basically what we're looking at here is an educational-based data set. And if you actually get to the back of the handout, I don't know if you know about this, but UCLA has an amazing website. It's the UCLA Statistical Computing Portal. It's an amazing website. It's got a ton of resources. So, we're gonna steal some data from that. Okay? But what we're looking at here is we're looking at the relationship between whether or not a kid has a high quality, is going to a high quality school, trying to be predicted by the parents' average level of education. Okay? And what we have here is we've used the logit command instead of the logistic command. And we have some output here, which looks a whole lot better than the data that we've been using. Look at that chi-square. What kind of R-square is that? Fat R-square, right? There's a gazillion of them. And I'm gonna point you to some to a program that we can download from within Stata to get all kinds of stuff. All right. So we're there. All right. So I'm going to flip back and forth between the two, between the Stata and the presentation, right? So what we're trying to do here is we use maximum likelihood to make these estimations, these coefficient estimations, estimate our coefficients, right? And we report log likelihoods. Log likelihoods. So by taking the logarithm of these things, we make them bigger. And what we're going to do is we look at these logarithms as sort of like an overall F statistic, like in the ANOVA. Okay. Okay. And we talked about McFadden pseudo R squared. There's a bunch of them, and I'll show you how to get more of them. And the other thing that we noticed when using the logit command is that the coefficients are in fact logits and they're not yet exponentiated. Right? But we know that if we want to make a prediction about a particular person, if we had multiple predictors, we have to use our logits and then exponentiate the sum of all those things, right? So that's why I like to start with the logits instead of going right to the logistic, which gives us our odds ratios. Okay. So what I'm trying to show here is that if we went in and did instead of using logit, we use the logistic command. Now the coefficients are exponentiated. The coefficients are now exponentiated for us. Even our confidence intervals are reported in terms of odds ratios. Right? So by using the logistic command,
So do you get the same answers as if you did the logistic OR?
Yeah. So if I do logit, and then do logit, comma, OR,
Yeah.
I get
It's the
this.
same thing.
Because all it's doing is it's taking those values and exponentiating it for us. right, so where did this value come from? I took the logit, I exponentiated the logit, now I have my odds ratios. Oh, so here's the other thing we want to notice here. Is let's take a look at these confidence intervals compared to these confidence intervals. This messes with people's heads sometimes. Right, so if I were to draw this distribution, right, because how would we interpret this? If we were to repeat this experiment an infinite number of times, we'd get a sampling distribution of this coefficient. We believe this is the standard deviation of that sampling distribution, blah, 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 right? The central limit there. We believe it would look something like this. Right? So really we would say like 3.9 plus or minus about 0.5 for our 95% confidence interval. Right? So the logits, these are going to be nice and symmetrical for us. But when we exponentiate these values, things start getting goofy. Right? So that 48 is not in the middle of these values, in the middle of our confidence interval here. Anybody have any insight as to why our confidence intervals from our logistic regression are not symmetrical?
The shape of the curve?
The shape of the curve is different, right? And the other thing is with our logits, the lowest level of a logit is going to be what? Negative infinity. And the maximum value of the logit would be positive infinity. Can I have a negative odds? Can't have a negative odds. Smallest odds is going to be 0. Right? So this is a nonlinear transformation. Right? So that's something to keep in mind. Okay? All right. What do we want to talk about next? Okay. So when we did regression before, we had all of these kinds of post-estimation commands, and one thing that we could do is we could predict the y-hat, right? So the y-hat, what do you think the y-hat's going to give us in this case? After we do our logistic function. So what it's going to tell you actually what it's going to give you. It's going to give you the probability of a high quality education. So look at this. We get an average probability of 0.32. We'll do that. The other thing I want to do is I want to do a fit a scatter plot here. So what do you think that is? This is the logistic function that we fit to the data. Right, so what we're saying is as the average number of years in a parent's education increases, what happens to the probability of their child being in a high quality school? Goes up like a lot, right? What happened if the curve were the other way, though? What happened if the curve looked like this? What do you think the sign of the coefficient would be? The sign of the logit?
Negative.
It'd be negative, right? What would the log odds be? What would the logits be? Or I'm sorry, not the log odds. The odds ratios be?
Less than 1.
Be less than 1, right? Okay. I'm sick of typing. My fingers are too big for this. So what I want to do is I'm going to put these two curves together. So this is where we begin to see this sort of separation here. So, right, so we see, what do we see? Most people who have sort of this much education or less, so we have people who have kids who are not in the high education, not in the high quality school system, kids in the high quality school system, right? We see a shift in the distribution of those points, right? Everybody see that? And the other thing that we see is once we get above sort of this point here, this number of years of education, it's all but, you're all but assured to be in a high quality education system here, right? So what I want to talk about next here are these things about, along this curve, along the function that we just observed, the probability are not exactly, they're not perfect, right? Our classification or our prediction as to whether or not somebody was in a high quality school system or not was not perfect, right? So if I were to draw this is probability of a high education. This mark becomes 50, the 50% probability. Here's 0, here's 1. What we can do is if we were to change the cut points in our classification, right? If we were to change the cut points of being able to predict whether or not somebody was in a high quality school system or not based on education, then our sensitivity and our specificity would change, right? Make sense? So if I made it such that our best guess is, well, if you had more than 3.5 years worth of education, we would have a high degree of specificity, right? But a very low degree of sensitivity, right? Make sense? Yes? Okay. This is what I'm trying to demonstrate here. So what I did here was, this is our predicted value based on our logistic regression. This is the observed values of whether or not they went to high quality high school. Right, so we can change these values at whatever cut points that we want. And we can see the effect, because we were talking about clinical decision rules before. These are how clinical decision rules are developed. Right, by changing the different cut points as to whether or not we decide whether a person is, positive, not positive, or sick, not sick, whatever the case may be. This is how it works. So by using that ESTAT classification that I showed you guys before, we can get the sensitivity and specificity and the positive and negative prediction values here. Right? Make sense?
When you specify the 0.5 and 1, what is that indicating?
It's giving ranges. So it was 0.5 and then 1. So what it did was, it took the probability that goes from 0 and 1,
Yeah.
and it said, okay, at 0.5, anybody from 0 to 0.5 is going to be in this group. Anybody from here to here is going to be in that group.
So you dichotomized it.
Yeah. Because remember, these are probabilities. Right? It's a predicted probability. So if I said, well, there's a 30% chance that you're going to be in a high quality school, that's a 30% chance. As opposed to saying, given your characteristics, are you more or less likely to be in a high quality school? Right? So by taking that 30% or taking 0.5 as the cutoff, we get this level of sensitivity and specificity, this level of PPV and NPV. We could change those values.
Would you want to though? I mean, like, is that generally what you do for a logistic regression? When it's like,
Well, it depends on what you're trying to do, right? So the idea here is,
like, would this be sort of a standard approach?
it's
here?
helping to think about how well does your model do at making your predictions. So 0.5 is sort of, that's the coin flip, right?
Mm-hmm.
So that's the standard approach is how well did you do as compared to a coin flip. Could you increase the sensitivity and or specificity of your model? Sure you could. It's hard to do both simultaneously, right? So if you don't change the inputs of your model, if you don't change the inputs of your model, then you have, and you want to increase the specificity, then by definition your sensitivity will go down. Right? Because you're saying by making it more sensitive, you're saying more people have the condition. So you'll have a higher false positive rate, which then messes with your specificity. So this is the sensitivity curve and the specificity curve, right? So if I wanted to maximize the probability, the prediction power of my model, instead of setting my classification at 0.5, what I could do is I could find the point at which these two values cross, and then this would give me the maximum sensitivity and then maximum specificity of the model. Does that make sense? Because what's happening, the more specific I make my model, as my specificity increases, what's happening to the sensitivity? It goes down, right? So in this case here, where I'm saying everybody goes to a high quality school. Have I captured all of the people who went to a high quality school? Yes, I have. But I've also captured all of those people who went to a low quality school. Right? And the same thing is true by saying nobody went to a high quality school. Did I get the negatives right? I captured everybody, I properly classified everybody who in fact went to a low quality school by saying that everybody goes to a high quality school, but I didn't classify the other group correctly. Right? So by looking at this, we can figure out, well, what is the point at which our sensitivity and specificity is maximized? Instead of coming out with a probability of 0.5, what we would then do is we would say, okay, the probability at, let's call that 0.25 or something like that. That would be the point at which anybody with a probability of above, say, 0.3, we would say they're most likely to go to a high quality school, and then our predictions would be best.
So what's the code for that?
I'm sorry?
How do you get that graph?
To get, oh, it's LSENS. It's in the
Oh, okay.
And how do you get the exact number
How do you get that exact number?
instead
Just
of
eyeball it.
There is an exact way to get the number. I'll write it down for you
Okay.
at some time. When you guys learned about doing diagnostics and stuff like that, you didn't learn how to do all this?
What do you mean
Diagnostics?
I actually learned it from like some research project, but I never had to. I never
Really?
learned it in medical school.
I don't think.
I
What
mean,
do you
like
mean
general
by
science,
I don't-
sensitivity
This is the same thing that happens with the test, like a lab test. It's the same concept.
I mean, I think we learned the concept there's,
Yeah.
I think we learned the concept there's a trade-off and that there's like a point at which you're gonna maximize
But not-
both, but
not like formally.
not like.
But didn't figure out how to do it.
Like RC curves, no.
Oh, okay. What'd you say?
like, if we get this graph, shouldn't data be able to easily
Yeah.
tell me what that number is?
Not necessarily, but there's a fairly simple formula. I'll write it down for you. Bring it in now. Okay, then the next thing I want to do is I want to show you about ROC curves. So if I type in LROC, LROC, this gives me my area under the curve. Right? If my test were no better than a coin flip, then these dots would go right on this 45-degree line. If my dots were below the 45-degree line, then we have a terrible model. It's no better than flipping a coin.
Of course, yeah.
It's worse than chance. So in this case, you know that the infinite number of monkeys banging on a typewriter, they would do better. Right? So the other thing that Stata does for you very nicely is it calculates the area under the curve here for you. So the area under the curve would be, the potential area is from, it's this rectangle here. Okay? It's that rectangular area here. Some authors report this area of the curve as a C statistic. So optimally, we would like our C statistic to be as close to 1 as possible.
Oh, okay.
Now, with respect to this, there's a whole other course on clinical decision making using data. But the idea here would be to think about what are the costs. This happens a little bit, you know, there's always it seems like an annual argument every year about mammograms as to whether or not to include that in healthcare plans or something like that. So this is where the argument comes from. So the idea is, yes, if I catch somebody, if I screen all the women in the United States and happen to catch one of them, right, then I've potentially saved that woman's life if we could do some early intervention with respect to the condition. So by doing all of that testing, and suggesting that having a very high level of sensitivity, we're going to catch more people who have the condition, right? But at what cost? There's going to be the cost associated with, there's going to be the labor cost, there's going to be the machine cost, maintenance cost, all of those costs associated with the higher number of tests and a higher level of sensitivity. However, if we increase the specificity, that is increasing the probability of getting the negatives, right? There's going to be another cost that could be either saved or, in this case, there would be cost incurred, right? Because for those women who would not be tested or didn't have such a sensitive test, there would be a cost. There would be not only the cost of the life of that woman, but also the cost of treating that woman. Because we maybe didn't catch it in the early stages of the breast cancer. We caught it at maybe stage 4 or something like that. So we have to do something radical, which always costs more money, right? So with respect to clinical decision making, we have to decide what function do we want to minimize or maximize. And then what is the point on the curve at which that function is maximized? We're always maximizing things because you can take the inverse of something and then that would be the maximization of that minimization. I'm going to teach it max. But there's, you can, that's a whole other course, clinical decision making. So there's also another way that we can examine our models, and it's called the Hosmer and Lemschau goodness of fit statistic. And essentially what it's going to do is it's going to take your group and it's going to chop it into 10 categories. And it's going to cap it up, and it's going to chop it up into deciles by probability. And then it's going to fit, the other dimension of the table is going to be whether or not you truly were positive or negative with respect to the outcome. If you change that 10, it would just have more or less fewer or more categories here. But what we're looking at here is really a 2 by 10 chi-square table. Make sense? Remember, a chi-square, we're looking for test of independence.
The groups are by the problem.
So what we have, the groups are, so these are deciles of probabilities.
Okay. And the number, does that reflect the cut point?
Yes,
Wait, which number?
these numbers here.
Those numbers.
All right, so in this case, we don't want to reject the goodness of fit statistic. We want our chi-square to be large. The hypothesis we're testing using this approach is we're saying that this is a good model. We don't want to reject that hypothesis. Fair enough?
What do you do with the rest of that table?
Okay, so do you remember how to do a chi-square statistic?
Theoretically, yeah.
Theoretically, okay, so.
It's like tab, or something.
A tab.
Call the chi-square.
Yeah.
Let's do a quick chi-square. So the idea of a chi-square, we'll do a simple 2 by 2. We'll do male, female, high quality, low, not high quality, right? And we'll see if if sex is independent of the quality of your education, right? So just give me some relatively small numbers. 5, 2, 1, 4. Okay, so what we're going to do here is that in the chi-square distribution, the assumption is that our margins here are going to be fixed. Okay? So what we're going to do is we're going to say if these things are independent of each other, it doesn't matter which row or column you're in, they should basically be uniform. Right? These 12 observations, these margins should be uniform. So what we can do is we can compare the observed minus the expected divided by the total, which if we were to write that all out, it looks kind of sort of like a standard deviation. So the observed for this cell is going to be the product of the margins divided by the total. So what's 42 divided by 12? Whatever the hell, it doesn't matter what it is. Right, but then I would do observed minus expected divided by the expected under the summation, and that's a chi-square statistic. All right, so what do we have here? Here we have the observed number of people. Here the expected number of people for each of the groups. I sum that up, the sum of this is going to be my chi-square statistic. There are 8 degrees of freedom because there's going to be 1 degree of freedom for my condition. My yes-no condition is 1 degree of freedom. And, okay, whatever. So we got that, right? So here we want a high. We want a big p-value. Anything above, the magical 0.05, we would say is a good thing. We cannot reject the hypothesis that this is a good fitting model. And I hope the air conditioner's on tomorrow.
It's gonna be cooler tomorrow.
Pardon?
It'll be cooler tomorrow.
Okay, good. Okay. So there's another program that I want you all to download. And what we can do is I want you to type in SSC install FitStat. FitStat. Here. SSC space install space FitStat. So what that's going to do is it's going to go out to this site, I think it's up in Boston, and it's going to download and install this program for you. So after you install FitStat, type FitStat, and you should get this table. So there are many more indices of fit for these kinds of models. And FitStat sort of gives you a smorgasbord, but there are still even more.
How long will it know that we're talking about the same regression?
Until you do something else that is going to have a different model in memory.
Okay, so until I do another thing that has a logistic or a regress command?
Yes, something
Okay.
like that. Or if you were to type mean, that would have another another beta matrix in the memory.
Okay. So as long as I keep doing stuff that's related to the regression.
Yes, then you're good, all right? All right, so anyway, so the idea here is, remember we talked about likelihood ratio tests? If not, we're going to talk about that more. And we said we compared our chi-square statistic to see if the model was better than an intercept-only model. Okay. This is the likelihood ratio, the log likelihood ratio for that intercept model. This is the log likelihood ratio of the model that we fit, right? If I were to take -2, multiply them by take these two things, multiply them by -2, take the difference, I would get this. This is the likelihood ratio that we believe is chi-square distributed, comparing the model that I fit versus the intercept-only model. This is the p-value associated with this likelihood ratio statistic that we believe is based on 1 degree of freedom. The reason it has 1 degree of freedom is that we had an intercept-only model which had 1 parameter. Then we fit another model that included average age or average education, which had 2 parameters. It had the intercept and that other parameter, the average education. So the difference between the 2 models was 1 parameter, 1 degree of freedom. So we say that this is distributed as a chi-square statistic with 1 degree of freedom. That's enormous. This is the p-value for this chi-square statistic. This is McFadden's R-squared. This is the R-squared that Stata actually reports for you. And right, because you got to have an adjusted one. Ignore all this, right? The reason I wanted to bring your attention to the idea is that Stata reports of McFadden's R-squared is because there's lots and lots of them. There are many of them. So if you want to be an unscrupulous researcher and make your model look better or worse, well here, look at this. There's quite a discrepancy between these 2 things. However, we still interpret them the same way. Which is why I'm encouraging you to report which R-squared you're writing.
How do you choose?
Huh?
How do you know which one to do? Because like I'm looking up here, there's another one above.
Yeah. Oh, yeah, there's tons of them here.
Like there's this Hosmer
Oh, yeah.
Lean show.
Yeah, Hosmer-Lem show. The Hosmer-Lem show is, that was the other one that we did. That was a chi-square statistic.
Yeah.
For the goodness of fit.
Are they always going to be discrepant in the same way? Like, is one always going to give you a more conservative R-squared than another? Okay. So you know if you want to be more rigorous, you can use, I guess, like the McFadden's because it's the, or which one is this?
Sort of in the middle.
Sort of in the middle. Okay.
Yeah.
What's the one that we learned like in basic statistics?
You learned the Pearson product
Pearson.
model, Pearson, which is different. The reason that we can't use Pearson's R-squared here is because this is nonlinear. It's nonlinear. Other things that you're going to you may hear about, you'll probably hear about more as time goes by, are these 2 things here. This is an AIC, that's not an A1C. This is named after a Japanese researcher. This is Akaike, that's his name, Akaike's information criteria.
I like that.
Yeah, me too. It's just a fun thing to say. Akaike. And BIC is the Bayesian information criteria. So this allows us to compare one model versus another, right? In Stata, in most software, we want these information criteria statistics to be big. Now, if you notice, if I compare the AIC for the small model compared to the big model fits better. Here's the BIC from the original model. Here's the BIC from the full model. Even though it's negative, this is still bigger than this. Right? Some software programs flip it around. So if you are going to use a different piece of software, understand how they're reporting and how to interpret their AICs and their BICs.
But it's always comparing an intercept-only model with your model?
No, we could actually fit a third model where I could add another variable, and I could do a formal statistical test to compare it. I could do the likelihood ratio test, right? Or I could compare the AICs versus each other. All right, so let's think about it this way. If I wanted to compare, just ask the question, what's a better predictor of my outcome? Is it parents' average education or is it the sex of the kid? Right? One thing I could do is I could fit a model with just the average education and get an AIC and a BIC, and then I could fit a second model with just sex. They're not nested within each other. Right? So I can't compare the models directly. I can't do that likelihood ratio test that we learned to do.
Like that estimate thing.
Yeah, exactly. I can't do that, so how am I gonna compare these two models? One way to do it is to compare the relative size of these these fit statistics. So you would choose the fit statistics with the higher value. And as you go into different kinds of models and different types of statistics, in structural equation modeling and confirmatory factor analytic work, which I do a lot of, there's probably 50 or 60 goodness of fit statistics, and none of them agree with each other. Like, they're all different. So my advice is to say you're going to report the pseudo R squared, you just report that it's McFadden's R squared if you're going to use Stata. The reason I'm showing you the fitstat command is that these AICs and VICs become important for comparing non-nested models. Okay. All right. So we've been talking about these concept of nested models here. So let's make this a little bit more concrete, okay? So let's say that I have a simple model. In this case, I have model A, right? I'm going to have model A here. And in model A, I'm going to fit the parameters. I'm going to estimate the parameters for variables x1 and x2. Okay. So, and then I'm going to fit another model where I'm also going to include x1, x2, but now I want to include x3. And so the question becomes, the question that we could ask is, does adding x3 improve the fit of the model? Does it do a better, how much better, is it worth it to make a more complex model? Right, if we think back to the tenets of basic tenets of science, is that science seeks parsimony, right? Right, so two competing models that are equally as good, we ought to choose the model that's simpler. Right, that's one of the goals of science. So how are we going to do that? There's a couple of ways that we can do that. We've talked about the likelihood ratio test. Another way of doing these things that we haven't talked about yet is something called a walled test. And a walled test is also going to be a chi-square test. And there's something called the Lagrange multiplier test. Right? You'll see these Lagrange multiplier tests in other places. But these are, we'll talk about this. So if you can grab this other data set and download it. So what this is the high school and beyond data set. Are you guys familiar with the high school and beyond data set? High school and beyond data set is a longitudinal survey of a bunch of students that were in school, I think in the 80s, and they measured these guys and gals very frequently, many ways, and they looked at all kinds of different outcomes. So this is kind of, sort of, similar to a data set that you guys might be using. These longitudinal panel surveys. And this is a random sample of 200 people. So That's what we're looking at here. So what we're looking at here is a variable called high right. And what we want to do is this is a score, it's a categorization as whether or not their writing scores was above the average. And what I'm interested in doing is I'm looking to see, well, what predicts as to whether or not somebody has above average writing skills. And I'm going to use sex and a reading score to try and predict whether or not they have an above average writing score. Okay, so just for some practice here, looking at the coefficients, what can we say? You can tell a lot just by looking at the sign of the coefficients.
Both positive.
Both positive. So being a female is
More likely
relative to
being male.
males in having a higher reading score, a writing score above average, right? This also says because the coefficient for reading, this is your reading score, is positive. This says that the higher your reading score, the more likely it is that you're going to have you're going to have an above average writing score. Make sense? Okay. So a male who gets a 0 on their reading test, they have no shot in hell of having an above average writing score. So that's how I would interpret that constant, right? The intercept. So what I'm going to do, and we did this before, is I'm going to store the estimates for that model. So that's in memory. This model, all this information about the model is in memory. The coefficients, the likelihood ratio, all of that is in memory. And I called it M1. So remember, we used these estimate commands before, and the syntax is estimate store, give it some variable name, whatever you want to call it, right? And the other thing I can do is I can say, okay, what estimates do I have stored in memory? That's what estimate dir does. Estimates replay is to show back what we have. So let's do that just to see how these things work. So I type in estimates dir, and it's going to tell me, well, I have a variable in there called a set of estimates that I'm calling M1. It was created from the logit command, and it tells me what the dependent variable word was. It tells me how many parameters that I have. Right, so fit 3 parameters. If I type in estimate replay, I'm able to recreate the table.
Do you have more than one estimate sort in there, or do you do all of them? Or
If you typed in estimate dir, it'll give you that table of the list of the variables and all that stuff. Yeah. To type in estimate replay, it would do model 1, model 2, model 3, model 4. Which is helpful if you want to present more than one model and put them together somehow. So here's what I want to do. I'm going to fit another model. But with this model, instead of just having female and read, I'm going to include math and science scores too. All right? I'm going to fit math and science scores too. So this chi-square is going to be based on 4 degrees of freedom, where the previous one was only based on 2, right? The first model that we fit is nested within this model because it contains all of the components of that first model. Does that make sense? So that's what we talk about. It's models that are nested. Sort of the parent model contains all of the components of the child model. And I'm just going to store this by saying estimate store M2. Now I can compare the 2 models. So my hypothesis, the null hypothesis that I'm testing here is that those new parameters do not improve the fit of the model. The new parameters do not improve the fit of the model. So notice the likelihood ratio, or the difference between the -2 likelihood ratio, is going to be 36.5, 36.05. If I were to take the log likelihood from model 1 and the log likelihood of model 2, multiply them both by -2, then take the difference, I get this. It's got based on 2 degrees of freedom, because the big model had 4 parameters, the child model had 2 parameters.
Sharon, can you say one more time how you interpret that? So it's like,
Yeah.
it's just saying that they're different?
Yeah, so not that they're different, it's a fundamentally different question. What we're asking is adding the extra parameters, does that improve the fit of the model? Right? Does that really give me anything above and beyond what I already have? Does that language sound familiar? Some of the partials? The hypothesis is no. The more complex model is not necessary. It doesn't add very much. The small p-value says, well, statistically speaking, we're going to reject that null hypothesis that the extra parameters don't do anything. In fact, the data suggests that those 2 parameters that we fit, those 2 extra variables, actually gave us a lot. It improved the fit of the model significantly. So if I were to take the difference between the likelihood models here, the first model had 3 degrees of freedom, the second model had 5 degrees of freedom. 3 minus 5 gives me 2. That's where the 2 degrees of freedom came along. Now here's another thing I can do. What this walled test does, this is another way of asking the same question. So what we just did was a likelihood ratio test before, and what I've just done here is called a walled test, W-A-L-D.
Just by doing this quietly.
No, I refit the model. I had to refit the model because I was doing other test statistics, so I put that model back in memory again.
You don't have to do it quietly, right?
No, I don't have to do it quietly. We'll just take up more stuff on the screen.
Got it.
Okay?
So, okay.
Okay. So what I'm going to do here is I'm going to use the test command. Right? And these are the two new variables that we've added to the equation. And this is a joint probability test. This is a joint test. What the walled chi-square, what the walled test does, it says, do these two things together, are those two variables together, are the effect of those two variables together 0? That's what it's asking.
Is that for any number, or do you basically do that on whatever variables you've added to a model? Do you do
Whatever variables I have to do.
It has to be more than
Shouldn't
one.
be
I'm sorry?
so if their LR test is significant, shouldn't this be significant?
Yes, but not always.
And it has to be at least 2 parameters?
No.
No.
I could add a model one variable at a time, build a model one variable at a time.
If you just added one at a time, would you still have to do the?
Yes, because I'm still asking, is that value 0? So they're asking sort of the same question differently. Okay. Then there's going to be 2 more commands that we're gonna get. Opt.
Sorry, one more on that. It's an all or none though. Like if you have a model and you add 5 variables, you do it on all of them or
No.
or-
So the answer, the question I asked is because I added 2 extra variables at that step.
Right, but it's whatever you've added at that step. You
Yes.
don't run out part of what you've added.
Correct. Yes. So something else that we want to do, I don't know if you guys know the find it command. So I typed in find it enum opt. So if I type in find it enum opt, that's just a funny thing to say. It's going to go out to the Stata website and say, can it find this program out somewhere on the internet? So I can find it here. What I'm going to do is I'm going to click on this little blue part here, and then it's going to say, well, click here to install. Bada bing. Then I'm going to get the ancillary files too. I can close that down. Then another file I want to grab is called test omit. I'll do the same thing here. Oop, no matches with that. Okay, well, never mind. Okay. So what we're going to do here, I don't know if this is going to work. Yeah, it's not going to work here. Never mind. All right. Never mind. We got to skip forward because I can't find that. Okay. So another way is to do this is to use the nest reg command. Right, so this is sort of a very straightforward way of doing these tests here.
UCLA said test is no longer available.
Yeah. Okay.
Do you have to rerun the model before doing the
it's because it's going to do it for you. So remember we talked about fitting sets of variables into the equation? Remember we talked about that a long time ago? This is what NestReg is going to do for you. And it's going to say, okay, how much do things change as you're adding more things into the equation? So the one thing that you'll notice here is that the order in which I specify variables matters. Okay, so the first thing it's going to do, it's going to fit a model. The first segment is going to fit a model where it's going to predict gender from your reading score. Then what it's going to do is it's then going to fit another model with the second things in parentheses.
Instead of reading?
No, it's going to include
It just includes that.
reading, so that's that first set, and then your next set in parentheses. So this really operationalizes that idea we've been talking about testing.